Good afternoon, dear students. You are welcome for lecture on the EduSat, and today's topic is purpose of clamping. So, in our engineering field, we see that when we use fixtures or we are doing some machining operations like milling, drilling, and some other operations, or maybe for assembly, we need to clamp our job. The semi-finished components are required to be clamped on the working table, and after that we can pursue with the machining operations. So, basically we need to first of all understand what are the clamping systems. So, here is a very simple system of clamping shown. On your right hand side you see a clamp over here. So, you can see it is touching with the radius surface over here. Some radius is there, some contour is there on the clamp on the left hand side, and on the left hand side you have the workpiece which is to be clamped before the operation. Over here the operation shown is of drilling a hole. So, as we can see over here, the clamp is implying more pressure or force on the job. So, the job is getting distorted over here. So, the hole which was to be done in this job will not be at right angle to the job surface. It is likely to be made at an inclined angle, or it may have a curvy axis. So, we need to take care that these kind of things should not be there. The jobs are to be fitted in a proper way, and for the clamp over here, the material used should be medium carbon steel, and it should be hardened up to 50 to 55 Rockwell hardness. So, for high rate of production, we need a quick clamping system. It should be very efficient, and it should reduce the time of usage of the clamp. So, we need these clamps to resist the cutting forces when we are doing some machining, or it should resist any movement while we are doing some welding of different components, or even in painting the clamping should be quick and reliable. So, clamping elements hold the workpiece firmly engaged with locating elements during the operation to be done on it. Operation may include some type of machining like drilling, milling, threading, grinding, or welding or assembly. The clamping system should be strong enough to withstand the forces developed during the operation. At the same time, the clamping forces should not dent or damage the workpiece. Speed of operation, operator fatigue, and strategic positioning are other important considerations for contriving a clamping system. So, we should look into what are the basic principles that are to be kept in mind while using the clamping system. Number one is the positioning. Positioning is very important because the machining operation should be done at the right position. For that, we need to fix the job with some reference system properly. So, clamps should be positioned to direct the clamping forces on strong supported area of workpiece. Clamping on unsupported and slender area can bend and damage the job. This affects the accuracy of the operation and hence the part. For example, as shown in a figure, a vertical hole drilled in bent workpiece may become wavy or angular on release of the clamp. As the workpiece springs back to original shape as shown in figure with help of dotted line in figure 1, the clamping system should not obstruct the path of loading and unloading of the workpiece. So, the clamping system should be such that it does not obstruct the loading and unloading of the job. It should keep the area of workpiece free, so that the workpiece can be easily loaded on the machine table. So, what we have discussed right now was regarding this figure. Over here we see the clamp on the right hand side, and because the force of the clamp is large, the job is being bent over here, and this is a delicate job over here. And moreover, if we tighten this clamp with hex nuts with the threaded forcing, that is very likely to produce a very high force, which is likely to make the delicate job bend like this. So, we can see these dotted lines over here, which show the hole which is to be made in this job, and if the force of the clamp is more, the job is likely to deflect like this under the load or the pressure, and the hole which will be done over here will have an axis which will be curvy or it may be inclined, and it will not be at 90° to the job surface over here. So, we need to take care of this, that the clamping force should not be very high, and some kind of support could have been put from underneath this job at this position. The clamps in path of loading should be retractable or swinging, so that clamps can be withdrawn or swung clear of path of loading the workpiece as shown in the figure. So, as we discussed, clamps should not obstruct the path of cutting tool. Clamp should not get drilled or milled or machined or welded during the operation. So, while designing the clamping system, we have to take this into consideration, that the clamp itself may not prove to be an obstruction to the machining tool, that is maybe a milling cutter or maybe a drilling machine, or on the other side, if we are welding 2 or 3 components together with help of a fixture over there, the clamping system should be such that the welding is not formed on the clamping systems. So, other principle of good clamping system is discussed with the topic over here, strength. So, the clamping system should have adequate strength to withstand all the machining forces or any distortion that may take place while the metal gets heated up due to welding operation. The clamping system should be capable of holding the workpiece against the forces developed during the operation. The clamping force should not dent or bend the workpiece due to excessive pressure. The clamping of weak or fragile workpiece, clamping forces should be divided over wider area of workpiece. So, if the workpiece is delicate, we can increase the number of clamps, maybe from 2 it can be done up to 3 or maybe 4, it depends upon the job. If it is delicate, we can increase the number of clamps. While clamping soft workpieces, clamps should be fitted with pads of soft material like nylon or fiber to prevent damage or dent. So, next principle of clamping is productivity. So, we need to have a very effective system of clamping to give us high productivity. Clamping time should be minimized by using knobs, tommy bars, knurled screws, hand wheels and handles, so that clamp can be tightened or loosened manually and quickly without use of spanners, as spanners require added motion of picking, aligning and laying it down after the use. So, over here you are seeing some of the systems which are used for fastening in case of clamping. In the number 1 figure over here is the handle. So, if we rotate this handle, because screw is formed over here in the hole, as we rotate this handle, it will keep tightening the job. So, this is one of the easiest method of clamping a job without need of any spanners, and in the second figure you see a knurled head over here for the screw. So, this also does not require any special spanners to tighten this. While we rotate this in clockwise direction, this pad, resting pad, will be moving to the right hand direction. So, because this is not requiring any spanners, you can do it with hands. So, to be able to do it effectively with your hands alone, this surface over here is knurled, it is having knurling. So, it does not slip while you tighten it or loosen it with your hands, bare hands. And over here you can see a knob over here, hand knob. So, it is having a surface over here for the knob in such a way that you can hold this knob very tightly with help of your fingers, and it is not likely to slip. As you see in the cars, some knobs are there to adjust your car seats. Similar thing is over here. This hand knob is easy to operate. You can produce enough force with the help of your hand itself, and you do not need any spanners. So, this is a very quick method for tightening something in the clamping system. If you need more forces, then you may do it with a Tommy bar. So, example of your Tommy bar use is on your lathe machine when you are doing it tightening a job with a 3-jaw chuck or the 4-jaw chuck. Over there you are using this Tommy bar. So, this is made from hard material, and the length of the bar is so much suitable that you can tighten to create a very big force to hold the job well in the chuck of the lathe. And another one is handle over here. A simple handle is there. This is also effective for medium forces. To tighten any job with medium forces, this hand operated wheel is a very good alternative. Then another principle which is to be followed while designing the clamping system to be taken care of is operator fatigue. So, the operator should not get tired after using these clamping systems too early. He should be able to operate without getting tired. Operator fatigue has to be taken care of. If a number of clamps are required to be loosened and tightened, then it will be better to use pneumatic or hydraulic clamping system. This will reduce operator fatigue as well as time required to operate. Power clamping facilitates tightening and loosening of number of clamps simultaneously. So, we have some drawbacks in operating with our hands alone. If there are too many clamps to be operated while fastening a single job with multiple clamps on the table, then in that case we can use a pneumatic clamping system, or if we require even more forces, then we can use the hydraulic locking systems for clamping. Then another principle which is to be followed while designing an efficient clamping system is workpiece variation. So, at many times we find that there is some variation in size of the workpiece. Sometimes there is more tolerance that is possible in the job pieces, and in that case the clamping system should be able to take care of these variable pieces. Some pieces may be thick and some pieces may be thin. So, some change may be there, the size may not be exact. In that case the clamping system should be such that it can take care of the thinner pieces as well as the thicker job pieces. The clamping points where clamp rests on workpiece and fixture surface, there should be a suitable radius to make clamp operable even if there is variation in size of job. Heel pin surface should also be made spherical to permit some tilting of the clamp. So, over here in this figure you find this clamp over here, the strap clamp. It is having a recess or a pocket in its center, it is a slot actually, and here you can see is the nut, and over this stud, as we tighten this nut, this surface over here will be touching the job work which is being tightened, and over here on the right hand side it is resting on the plate on which the job is being tightened or clamped, and over here the resting of the nut is over a surface which is circular. As this surface is circular, this clamp can be used for thicker or thinner job works. So, variation is possible in this as seen in this figure. So, this part is made with help of forging, because a forged part is better than the machined parts, and of course, it is better than the parts that are produced by casting. So, this forged clamp over here is a very good alternative and gives a very good reliable clamping. It is very forceful. On the right hand side, we have a figure in which we see on the right hand side is a spherical heel pin. So, the clamp is resting on this heel pin on the right hand side. It is acting as a spacer, while you see the workpiece over here, the surface where the clamp is going to touch the workpiece is this along the pen, as I am showing on this dotted line, and this clamp is having some spherical curvature over here, or rather it is having a circular curvature over here. So, if the workpiece is of thin or thick size, this clamp will be easily able to adjust it according to the requirement. Over here on the top, under this nut, we see two spherical washers. One is the male spherical washer and the other one is female spherical washer. In the lower one, it is the conical one, over which this convex washer can rotate a little bit. So, it is an adaptive design which is really required for to check out the variation in thickness of the jobs. So, this radius at clamping point is very important, and this kind of spherical washers are very important where you want adjustability for the clamping system. In this figure, you can see the concave washer which is to be fitted below the convex washer, and over this convex washer comes up the hexagonal nut. So, the hexagonal nut is putting pressure on this convex seated washer which rests on the concave shaped washer below. So, whenever this combination is there, the nut will be butting this convex washer squarely, that is, it will be very parallel to the surface of this convex washer. So, these are used in pair. Used in pair, two washers have matching male and female seats as shown in figure. The spherical bearing allows the washer to tilt with respect to each other. The lower female washer tilts with the clamp, while upper male washer below the nut can remain square with the nut. In multiple clamping, a pivoted equalizer is used for clamping two unequal workpieces simultaneously. So, for producing a system of clamping for multiple jobs with this system of pivoted equalizer, we can clamp two jobs in a single go. So, as we see in this figure, two jobs have been clamped over here. One is on the left hand side, other one is on the right hand side. And over here on this element, there is a pivot pin over which this triangular element can rotate a little bit. So, if it rotates in anti-clockwise direction, it will be touching on the left hand side job. If it is made to rotate in the right hand side clockwise direction, it will be putting pressure on the right hand side job. So, with this swinging action over here on the left hand side and the tightening on the right hand side with a nut with a prefixed bolt on the right hand side, which is again a hinged joint, So, this is creating flexibility in design. You can see 3 hinges over here, 1, 2 and 3. With this pivot pin design, you can clamp 2 jobs simultaneously, which are of different thicknesses. So, these are unequal work pieces, one may be thicker, one may be thinner, but because of this pivot pin, the tightening will be equalized on both sides. It will take care of both the jobs, even if they are having a slight difference of size. So, our next topic to be discussed is type of clamps. So, there are numerous types of clamps that we can choose from while we are designing the clamping system. So, all of these have to be checked or kept in mind, so that we can use the best alternative while we design the clamping system. So, let us discuss this types of clamps. The different types of clamps can be broadly categorized as follows: screw clamps, strap clamps, pivoted clamps, hinged clamps, swinging clamps, quick action clamps, multiple clamps, power clamps and unconventional clamps. So, we come across these hinged clamps very occasionally, because these are providing an advantage, as we see in this figure. In this pivoted joint type of clamping system, we are holding 2 jobs at the same time. So, this serves the purpose of quick action clamps, and of course, it also serves the purpose of multiple clamps. As far as the power clamps and unconventional clamps are concerned, over here we may be using pneumatic clamping system or the hydraulic clamping system, or in the unconventional type of clamps we may be using magnetic power also, where the forces involved for machining the workpiece are not more. Over there we can use a magnetic table, for example, in the case of grinding of surface of the workpieces. So, number 1 will be the screw clamp. Screw clamps are threaded parts with knurled collar, hand knob, tommy bar, etc., as shown in the figure. So, over here in the figure below, it is shown a screw clamp. Over here we can see there is a bolt with a hexagonal head over here. As we tighten this hexagonal head of the bolt will be driven downwards, and it will produce force over the job, so that the job does not move anymore. So, for this we need a spanner over here. And in the above example, which is for equalizer for 4 workpieces. So, as we want quickness in the clamping system, we are trying to clamp 4 pieces simultaneously in a single go. So, this will be pretty advantageous because these pivot points are there. Number 1 pivot point is there, number 2 pivot point is there, and number 3 pivot point is there. So, this main pivot point over here is controlling these 2 pivoted elements, one on the left hand side and other on the right hand side. So, by means of this kind of a system, we are able to settle down with 2 jobs or workpieces on the left hand side and 2 jobs on the right hand side. So, we can see we have done with 4 jobs simultaneously over here. The clamping area of screw clamp can be increased by provision of pad, because if the screws which we generally use for clamping may be ranging from size of 5 millimeter to up to 25 millimeter in diameter. So, it depends upon the force that is required in case of the job. For delicate jobs, we may require a screw with 5 millimeter dia, and for heavier jobs we may require about 25 millimeter diameter, which is actually operatable with your own hands manually. if we require force that is to be produced is more than even 25 mm of dia, in that case we will be using hydraulic system for provision of adequate force while clamping. So, when we are doing with these small size screws, say 8 mm screw or say 12 mm screw, when we tighten these kind of screws onto the surface of the workpiece, it is likely to create indenting over there. So, before the screw head actually touches the job, we can place a pad in between. The pad may be made of some soft metal like aluminum or copper, and sometimes it is made from nylon also, so that the screw does not produce any indent over the job. So, the clamping area of screw can be increased by provision of pad. This also eliminates friction between workpiece and pad. The clamping pad remains stationary on workpiece while screw rotates and rubs on surface of the pad. So, the force developed by screw that can be calculated will depend upon following factors. Number one is it is a force developed by the screw. This force developed by the screw will depend upon the following elements. Number one is Ft, which is pull or push applied to the screw, which means which is equivalent to the torque produced by this handle or the Tommy bar. So, generally this may be varying from 10 centimeter to 30 centimeter, this handle length where you are applying force with your hand. You may be for an example, you may be creating a force of 10 kg with your hands while you are tightening a screw of 12 millimeter dia. Then R is the pitch radius of screw thread. So, if the diameter of the screw is 12, the radius will be 6 mm, and then tan theta is there, which is helix angle of thread, and then tan alpha is there, which is friction angle of thread. Then L is the length of the spanner which we are using. So, in a typical example, a 12 millimeter hex head bolt with 100 millimeter long spanner and 10 kg manual pull can develop 700 kg clamping force along the axis of the screw. So, with a 12 mm hex bolt, you are able to develop enough clamping force, that is 700 kg for a single screw clamping, and if you increase the number of clamping points, you can increase the clamping force even more. So, next topic which is important while designing these clamping systems is to choose from different designs of clamps. Another type of design for clamps is strap or plate clamps. These are made from rectangular plates and act like levers. In a simplest form, the clamp is tightened by rotating nut or central screw. So, these strap type of clamps are made from mild steel in general, or they may be made from the EN8 or EN9 series of material, which is slightly superior to the mild steel, and these steels are hardenable. The EN8 series or EN9 series materials are little more superior than the mild steel, but in general we are using mild steel for the strap type of clamps. So, as the name suggests, we can see a strap clamp over here, which is a rectangular bar made from a plate, and in the front view we can see the system where this clamp is being used. So, there is a slot over here. In this slot, the strap clamp can move onto the left hand direction or to the right hand direction. So, over here the workpiece is fixed with the strap clamp, and after doing the job we will be rotating this nut over here about 1 turn or maybe half a turn. At that time this strap clamp can be retracted onto the right hand side. So, this area will become clear for loading of the workpiece again. So, in this retracted position of the clamp, we place the workpiece and again push the strap clamp onto the left hand side, so that it can butt on the workpiece, and then we gave about 1 turn on this nut, so that this strap clamp produces the force on the workpiece before we can do the machining. In the middle over here, over this stud or the threaded stud over here, you can see on the outer side there is a spring which is keeping the strap upwards.